So as we have been discussing about network growth models, and the last lecture we have understood why a synthetic network or a network growth model is important, right? So now let us start discussing a simple model for network generation. It's called random graph model or random network model. So this model was proposed by erdos-renyi, Paul Erdos and Alfred Renyi in a long time back actually, and it was one of the simplest models that we can think of for generating a random network. Okay, this is called ER. This is also called ER model. Your ER growth model stands for erdos-renyi, and it basically has two realizations. Okay, so let's first try to understand how this model works. It basically says that let us assume that there are n number of nodes. Okay, there are n number of nodes present in a network. We want to create a network with n number of nodes, but we do not know how the edges are formed, right? So what we will do, we will choose a pair of nodes and then we connect it based on certain probability, right? So say for example, we toss a coin. If the outcome is head, we connect the pair of nodes, otherwise we do not connect. Okay. So if you see, that is a very simple idea, of connecting pairs of nodes, but it turned out to be effective at least in satisfying some of the properties that real world network exhibits. Okay. So far we have discussed three properties. Let me remind you. One is it should have an high average local clustering coefficient. The second one is it should follow the small world property, meaning that the average path length should be proportional to logarithm of log of n, where n is the number of nodes. And the third one is a scale free property, which basically says that the degree distribution should follow a power law property. Okay. So there are two ways to actually explain the random graph model. One is called the Gn, k model, where n is the number of nodes and k is the number of edges that you want to create. Okay, and this is basically ER model that erdos-renyi actually proposed. It basically says that there are n number of nodes you choose and you want to create k number of edges. And how do you create? You just choose a pair of nodes, you connect it, and you keep on doing this thing for k number of times. There is no probability as such. But in this particular case, the number of edges will always remain same, right? The second realization is basically Gn, p, where p is the probability of connecting a pair of nodes. It basically says that you choose a pair of nodes and then with probability p you connect them, with probability 1 minus p you do not connect them. Okay, this was proposed by Gilbert in 1959. So both these models, in the asymptotic level, in the limiting case, both the models behave similarly, but in this particular chapter we consider Gn, p, okay, as the standard way to explain random graph model. Okay, so let's do some math. Okay, let's first try to understand what would be the, if we have Gn, p model, right, what would be the expected number of edges, expected or say average number of edges, right, that can be formed in the network G. Okay. So let us assume that the average number of edges is k. Okay. It means that there are n C2 choices, there are n number of nodes and there are n C2 pairs, possible pairs, and out of this n C2 pairs only k pairs have been successful in terms of connections. Okay. So each of the k edges which are formed, the probability is p. So for k number of such edges it should be p to the power k, and for nc2 minus k possible pairs, right, the probability would be 1 minus p, because because NC2 n choose 2 minus k, this number of pairs have not been connected, right, and the probability is 1 minus p, right. Now if you think of the the probability, right, this basically follows a binomial distribution, as you see, right. So it is basically p of k is in in C2 choose k, right, p to the power k 1 minus p to the power n C2 minus k. Okay, so this is the probability of k number of edges in a random network. Okay, so what is the expected number of so this since this is exactly following the binomial distribution, which is p of x, right. We know in Cx, right, p to the power x 1 minus p to the power n minus x, right, and what's the mean? Mean is always np, right. So in our case, if we take the mean number of edges or average number of edges of a random graph model, it should be n choose 2 into p, which is n into n minus 1 by 2 times p. Okay, so this is the average number of edges that you can think of in this particular model G n comma p. Okay, so if this is the average number of edges, let us think of the degree. Okay, so what's the degree? So we know that sum of degree is 2 into number of edges, here 2 into average number of edges, right. So let us assume that the average degree is this one, mod d, right. So if the average degree is mod d, what's the sum of all degrees? It is n times mod d. There are n number of nodes, and each of these nodes has on an average mod d degree, right. So this is 2 into this one, 2 into this one. I replace this by this, so this would be n into n minus 1 by 2 times p. Okay, this and this will cancel out, this and this will cancel out. So we will have average degree is essentially p times n minus 1. Okay, and this is also reasonable, right. You can I mean, in other ways you can also understand why it looks like this. Think of a node, right. So a node can have n minus 1 number of possible nodes with which it can connect, right. And all this, I mean, each of these pairs, right, each of these n minus 1 pairs, there is a probability p of connection, right. So actual number of pairs which are going to be actual number of nodes which are going to be connected with the particular node would be this one. Okay. So we have seen two things. One is that, so this is the, and you please try to remember these two equations, right, because you will keep using these equations later on also. So this is the number of edges, average number of edges, and this is the average degree, right. So what actually is, what other things we can infer? So as p tends to p goes towards 1, right, p is a probability, right. What would happen? So if this is 1, then the number of edges would be nc2, n into n minus 1 by 2, which is basically a clique. So p equals to 1 means what? P equals to 1 means we take take a pair of edges and we connect, because the probability of connecting a pair of nodes is always 1. So we will always connect. It is not the case that we will not encounter any case that the pair of nodes will not be connected. Okay. So as p increases, this will increase, right. We will also see that as p increases, the average degree also tends to be n minus 1, because ultimately it's a clique. So every node will be connected to other n minus 1 other nodes. Okay. So these two observations are important to understand. Now if you look at the degree distribution, right, so in case of degree distribution also we will follow the same thing, right. So we basically say that, look, we have n minus 1 number of, for every node we have n minus 1 number of possible cases, right, and let us say the degree is k, the degree of every we basically want to understand pk, right. Probability of a node having degree k is essentially n minus 1 choose k, p to the power k 1 minus p to the power n minus 1 minus k. Okay. So this is essentially binomial distribution, right, and we also know that as n tends to infinity, what happens is that pk starts behaving as a positive distribution, right. So e to the power minus say d, right, d to the power k by factorial of k. Okay. So essentially as you see here in this particular figure, right, this is the degree distribution of a random graph model, okay, with n equals to 1000 we have this kind of graph. When n equals to 2000 we have little bit spreaded graph, and when n equals to 3000 we have this kind of graph, right. So now the very interesting point that we discuss, okay, and this is basically called the the relationship of this random graph model with a giant component, right. So what is giant component? Now giant component is something that we discussed in the last class, I guess, or in the first lecture. We basically, giant component is a component, if you think of a graph as a disconnected graph, right, there are multiple components. A giant component is a component which actually accommodates 90% or 95% of the nodes, right, and other components actually have a small number of nodes. Okay. So when you have n number of nodes, right, and you basically choose a pair of nodes and connect, you keep connecting, right, when we will see that a giant component emerges. Okay. In other words, so since there is no restriction on the number of edges, we have only one parameter which is p, right. Since there is no restriction on the number of edges, right, can we come up with some relation either in terms of degree or number of edges, right, based on which we shall say that, okay, after this many edges or after this many average degree we will see a giant component, because initially all the nodes are disconnected, there are n nodes, they are disconnected. Then you choose a pair of nodes and with probability p you connect, otherwise you do not connect. So you basically start creating components, right. So when would be the case that a giant component will emerge? We will see that majority of the nodes will basically form a giant component, right. So we will try to come up with a theoretical solution for this, right. And interestingly we will see that in order to create a giant component or form a giant component, the average degree of a node should be 1. What I am trying to say is that if the average degree of a node is 1, you can see a giant component emerging, which is very non-intuitive, because degree 1 is a very simple thing. You can always see degree 1, right, but remember this is on an average, right. Some nodes may have higher degree, some nodes may have lower degree, but the average degree should be 1, and we will prove that when a giant component emerges, the average degree actually needs to be 1. Okay. So let's do it mathematically. So let us assume that there is a pair of nodes, right. There is a pair of nodes, say Vi and Vj, okay, and let us assume that Vi, so I am writing it slowly so that you understand it, okay. Vi is in the giant component, GC means giant component, okay. And let us assume that so if Vi is in a giant component, right, so Vi should be connected to at least one node in the giant component, because giant component is a connected component, right, all the nodes are connected, not directly but at least indirectly, okay. There is always a path, there is always a finite path between a pair of nodes, right. So then there should be at least another node Vj, right, Vj, which is connected to Vi, okay. So now let's think of some counter assumption, right. Let's think of say if Vi, okay, so you have Vi and you have Vj, okay. So if Vi does not belong to giant component GC, okay, it can only happen due to two cases, either of the two cases. The case 1 is that scenario 1 is that this edge Vi Vj, this does not exist, so this is not a part of E, okay, because if Vj is part of giant component and this edge exists, then Vi will also be a part of giant component. If Vi is not a part of giant component, meaning that Vi and Vj are not connected. So this is scenario 1. Scenario 2 is Vi Vj exist, right, but then Vj is not a part of the giant component GC. They may form a different component. So this edge exists, but then these two nodes actually form another component. They are not part of giant component. So either of these two scenarios can happen, okay. So let us calculate the probability that a random node V is a part of the giant component. What's the probability? So straightforward, this is the size of the giant component divided by the total number of nodes present in the graph, right. This is the probability. Let us define and say this is P, V belongs to GC, okay. Let us define another notation. Let us define M, which is 1 minus GC by N, okay. It basically says that what's the probability that a node is not a part of giant component. It's basically 1 minus the first equation, okay. This is M. So then if we know these two things, then let's try to understand the probabilities of these two scenarios. So what is the probability that the first scenario will occur? The first scenario is saying that Vi Vj are not connected, right. What is the probability that Vi Vj are not connected? This is 1 minus P, because P is a probability, because this is a random graph model. We have N comma P. P is the probability that nodes are connected, a pair of nodes are connected. So 1 minus P is this one. What is the probability of the second scenario, which basically says that the edge exists, but nodes are not part of the edge exists, but Vj is not a part of the giant component. So the edge exists, the probability is P, but Vj is not a part of the giant component, the probability is M. So this is P times M, okay. So these are the two probabilities. So now we can combine. So combiningly, we define that what is the probability, what is the total probability that the scenario 1 and scenario 2 will happen, right? P of S1 plus P of S2. This is essentially what? 1 minus P plus, right? What does it mean? It basically means that for a particular node, this is the total probability that it will not be a part of the giant component, okay, for a particular node. How many such nodes are there? Because we fixed a particular, we have already fixed a node, right? We have already fixed Vi. So how many other nodes are there? There are n minus 1 number of other nodes. So what is the, what is the total probability that n minus 1 number of nodes, are not a part of the giant component? This is basically 1 minus P plus Pm to the power n minus 1. Okay, so it basically says that the giant component will never emerge if this happens, right? So none of the nodes are part of the giant component. This is the probability. Okay, can we say that this is exactly same as M? Because M also says that the probability that a node does not belong to the giant component is this one, is M. So this is M exactly. Okay. So now let's do some tweaks, right? Let's take the log in both the sides. So we'll have log of M. We'll basically have log of M, which is n minus 1 log of 1 minus P plus Pm. Okay, and we already have seen earlier, if you remember in our last discussion, we have already seen that this one, right, that average degree D is P into n minus 1. So P is what? P is D by n minus 1. Okay, I will use this one here. So I know that P is mod D by n minus 1. Okay. So let us replace it here. So we'll have n minus 1 log 1 minus, right, let us take this common, mod D n minus 1, right, 1 minus M. Okay. So this is basically ln of 1 minus x, right. So when ln 1 plus x, we can approximate it as x when x tends to 0, right. If you remember the log curve, right. So as x tends to 0, so we have ln of x is basically same as x, right. So these are all these tricks are all, these kind of tricks are needed to simplify these complicated things, right. So we'll have, so ln m, so this is our x, okay, including the negative symbol. So we'll have what? We'll have this n minus 1 and this n minus will vanish. We'll have this one, okay, this one. Now let us assume another notation h, okay. What is h? H is the fraction of nodes in the giant component, right. Essentially h is mod Gc by n, right. This is also same as the probability of a node belonging to a giant component. This is same as h equals to, this is same as 1 minus m. M is the probability of not belonging to the giant component, so this is same as 1 minus m. Okay. So now let's come back here. So when we move log here, so this will be exponential, this will be m equals to exponential of, right, minus mod d 1 minus m. Okay. So what we will have? We will basically have right. So we will have now you basically subtract both a left side and right side from 1. So you will have 1 minus m equals to 1 minus exponential of this one. So what is 1 minus m? This is h. So h equals to 1 minus exponential of minus d. This is also h. So this is our equation. H equals to, so what is our equation? H equals to 1 minus exponential of minus mod d times h. Now we need to come up with the value of h, right? So I mean, how do we solve this equation? So there is no closed form solution. Okay, left hand side you see h, right hand side you also see h. So how do we solve this kind of equation? So we basically solve this equation using graphical format. Okay. So let us assume that this is y. Okay, y equals to h equals to this one. So you basically have two things. One is y equals to h, other is y equals to 1 minus exponential of minus dh. Okay, and this is your h and this is y. So y equals to h is this one. Okay, and how do you get the y value from here? So this curve is already plotted. What about this curve? So here you see there are three unknowns, h, y and mod d. So let us fix a value, say mod d. Say let us say mod d is average degree is say 0.5. If average degree is 0.5, then we vary h and we will get y. So we will vary h and we get y, and if you do that, you will see that it basically looks like this. Here this is mod d equals 0.5. Okay, we will see a curve like this when mod d equals to 1, right? And when mod d equals to 1.5, you will see like this. So this line, the straight line is y equals to h, and this other curves are this one. So what are the solutions? The solutions are those points where these curves actually intersect. So this is one point and this is another point. And how do you know the points? So we know that this kind of cases, we take the gradient, right, at this point, and then we at this point the gradients are same. Okay, and how do we get the gradient? So we basically take the derivative. So this is our equation. Okay, so I take the derivative with respect to h. What I will get 1 here, and I will get exponential of, right, minus, right, this is the gradient, this is the derivative at I mean with respect to h, right. And so since we know that at this point we have a solution, so let us put h equals to 0, because at this point h equals to 0. So if I put h equals to 0 here, what we will have? We will have mod d equals to 1. Right. So it basically says that in order to form, so this is what? This is average degree is 1. So it basically says that in order to form, or in order for an giant components to emerge, right, you basically need you basically need the average degree as 1. Okay. And if you think of it carefully, right, average degree is 1 means what? It means that nodes are connected to each other, right. Say something like this, right, average degree is 1. And if we have a line graph like this, you will also have a giant component. Okay. So the theorem is that a giant component emerges in a random network when the average degree of a network is greater than or equal to 1. Okay. In fact, you can actually based on these properties, right, you can actually think of different phases of a graph, right. If you think of it, you can actually plot a graph like this, where this is your degree, right, and this is the size of the giant component or the fraction, right. You will see that it do actually look like this. At mod d equals to 1, you see the giant component emerging, okay, and this is called phase transition. Phase transition. Okay. So this part of the region is called subcritical region. Subcritical region where mod d is less than 1. At d equals to 1 is called phase transition. Giant component starts emerging. Then this part is called supercritical region. Supercritical region where mod d is greater than 1, and this part is called connected component, when we will see that mod d is greater than log of n. Okay. And this kind of diagram is called phase transition diagram. Phase transition diagram. Okay. Let us look at the average path length, because average path length has relations with the small world property. Okay. So, and this is very simple. Now, so let's start with a node V. Okay. And what's the degree? Degree is mod d. Average degree is mod d. It means that in the first hop you will have mod d number of nodes, right. And let us assume that the maximum path length, meaning the diameter, is d max. Okay. So at the first hop we have d square d. At the second hop, again at every node has mod d number of nodes. So we have d square number of nodes here. Then the next hop d cube number of nodes here. In the last hop we have d to the power L max whatever. So this if you think of the path length is L max, the diameter is L max. So the last layer, the last hop, we have mod d to the power L max number of nodes. Okay. So and that constitute all the nodes. So we have one node in the 0th hop. The first hop we have mod d number of nodes. In the second hop we have mod d square number of nodes. Last hop we have mod d to the power L max number of nodes, and that is the total number of nodes in. Okay. So this is basically a geometric series, and this is right. So the sum. Okay. And you basically you ignore this part, right, minus at n tends to infinity when d becomes so large, then this does not matter. Then we will cancel these and this ones. We will have mod d to the power L max equals to n. You take log in both the sides, right, you will get this equation. Okay. And what does it mean? It says that, it basically says that the maximum distance, meaning the diameter, is proportional to log of n, right, which is exactly small world property, right. It is proportional to log of n. So the maximum one is this one. You can also say that approximately average distance between any pairs would also be log of n, proportional to log of n. So it means that the random graph model actually follows the small world property. right. So, it follows the small world property. So, one property is satisfied, but it does not follow the scale free property. Why? Because we have already seen earlier that it basically follows the Poisson distribution, right, or the binomial distribution, which is not a power law distribution. So, it does not follow the power law property. So, one property is ticked, other property is crossed, right. Now, let us look at the clustering coefficient, the last property. Okay. So, what is the local clustering coefficient of a node? Okay, now think about it carefully. So, it basically says that let us look at a node, and there are mod d number of neighbors, because the degree is mod d. So, what are the possible number of connections between mod d number of neighbors? This is mod d C2, right, and what's the actual number of edges? It is Bt times P, because the same logic, we have mod d C2 number of pairs, and then you connect these pairs with probability P, right. So, what is the clustering coefficient then? Clustering coefficient is possible number of edges, which is mod d C2, and actual number of edges, which is this one. So, these and these will cancel out. So, the clustering coefficient is basically P, and what is P? We have earlier shown that P is mod d by n minus 1, right. So, this is mod d by n minus 1, right, or n, whatever in the limiting case. It means that as n grows, if we fix mod d, if n grows, this starts decreasing the average clustering coefficient. If n is 1 million, for example, the local clustering coefficient would be extremely low, right. Now, this is opposite to the real world observation. In real world observation, we showed earlier that for a gigantic network also the clustering coefficient is pretty high, 0.14, 0.15 and so on. But it basically says, but in this case it says that with the increase of n, C will decrease, right. It means that the ER model does not satisfy the clustering coefficient property, right. So, it satisfies the small world property, it does not satisfy the clustering coefficient property, it does not satisfy the scale free property, which is the power law property. So, I stop here. In the next lecture we will discuss another model. We will see that how we can actually satisfy other two properties which have not been satisfied in this particular model. Okay? Thank you.